Okay, so in today's lecture, we will solve exercises again on chapter 16, and this is the last section, the last lecture on chapter 16. We solve two problems, one on speed of they are on speed of waves and on rate of energy transfer. Okay, so we will start with exercise 16.2. In your booklet, a wire is made by welding together two metals having different densities. So here we have to pay attention that I have one of them is 9 grams per meter. This is the mass per unit, mass per length. So mu1 is 9 e to the minus 3 kilogram per meter, and mu2 is 25 e to the minus 3 kilogram per meter. Okay, the figure below shows a 2-meter long section of the wire centered on the junction, but the wire extends much farther in both directions. Okay, so the wire is placed under tension of, so here I have the tension 2,250 Newton, then a 1,500 Hertz wave. So what is this? This is the frequency. And this is the tension. Okay. With an amplitude of 3 millimeter. So this is my amplitude is equal 3 millimeter, which means 0.003 is sent down the wire. Calculate the speeds of the wave in each of the wire 1 and wire 2. So we will start. So V1 is square root of tension divided by mu1. And this is equal because they said that the whole wire is placed under the tension 250. So the tension is the same, but what's changing is this mu1 and mu2. So this is equal to square root of 250 divided by 9 e to the minus 3. And this gives me 500 meters per second. And V2, it's the same, but mu2. And this is the square root of 250 divided by 25 e to the minus 3, and this gives me 300 meters per second. Okay, deduce the values of the wavelengths in each wire. So we will use the fact that the velocity is nothing but lambda. So this is lambda 1 times the frequency, implies lambda 1 is equal to V1 divided by the frequency, and okay, so let's see, so implies lambda 1 is equal V1 divided by the frequency, and this is V1, we just calculated it, divided by the frequency, 1,500 Hertz. This will give me 0.33 meter, and lambda 2 is equal to V2 divided by the same frequency, and this is 300 divided by 1,500, and this gives me 0.2 meter. Okay. Part C, how many wavelengths, that is complete cycles of the wave, are in this 2-meter long section of the wire? So I will look at each segment. So in the first 1 meter, I have lambda 1 is equal to 0.33 meter. So in 1 meter, how much do I have? In 1 meter, how many lambdas do I have? Okay, and I will get that I have 1 times lambda 1 divided by 0.33, and this is a 3 lambdas. That is 3 cycles. Okay. And then in the second 1 meter, lambda 2 is equal to 0.2 meter. So how many lambdas do I have in 1 meter? And I calculate this to be 1 times lambda 2 divided by 0.2, and this will give me 5 cycles. So in the first one, where mu1 is 9 grams per meter, I have 3 cycles. In the second one, where mu2 is 25 grams per meter, I have 5 cycles. So in total, I have 8 complete cycles. Okay. So we're done with the first one. Let's do the second exercise. A small steel wire of diameter 1 millimeter is connected to an oscillator and is under a tension of 7.5 Newton. So what do we have here? We have the tension, 7.5 Newton. Okay, so this is the tension. And I have a steel wire. So here you have to imagine, so I have a steel wire, so it is like this. Okay, so I have a steel wire. Of diameter 1 millimeter. So the diameter is from here to here. Okay, this is the diameter and it is 1 millimeter, which is 1 e to the minus 3 meter. This is the diameter as under tension. The frequency of the oscillator is 60 hertz. So I have the frequency F. And it is observed that the amplitude of the wave on the steel wire is 0.5 centimeter, which is 0.5 e to the minus 2, which is 0.005 meter. The density of the steel is rho equal 8050 kilogram meter per meter cube. So I have the density. Just want you to remember that the density from the unit, actually you can tell the density is kilogram per meter cube. So it is mass over volume. Okay. Okay. Show that the linear mass density mu, so the linear mass density is mu, could be expressed in terms of the steel density rho and the wire diameter d in the form mu equal pi rho d square over 4. So we want to prove that this is how I can express my mu. So let's start. So mu is nothing but mass divided by length, right? But mass, now I know from the density that mass is density times volume. So it is equal to density times volume of this wire divided by the length. Okay, now let's do the calculation for the volume here on the side. This is a cylinder. This is a cylinder, and the volume of a cylinder is equal to the volume of a cylinder is equal to pi times the radius of the cylinder square times the length of the cylinder. Okay, so it is pi times r, which is half d, times the length of the cylinder, and the length is nothing but this thing over here, from here to here. This is the length. Okay, so the volume is equal to pi times the r is d over 2 times the length. So the volume is equal to, I'm gonna do d over 2, this is a square. I'm gonna do, so this is pi d square, pi times d square times length divided by 4, because I have 2 squares, so it is 4. So I will come back here. So this is equal density times the volume, which is pi, times d square times length divided by 4 and divided by length, right? Because here I have divided by length. So it is 4 times the length. Okay, now what will happen? What will happen is that this length will delete this length, and I will have this equal to density is rho times pi times d square over 4, and this is exactly what I have here, pi rho d square over 4. So I proved part A. Actually, I can go a bit further and do the calculation. So this is equal pi times rho, which is 8050, times d, which is 1 millimeter, so that's 0.001 square divided by 4, and I will get mu is equal to 6. I'm calculating it because I will need it later. So this is 6.32 e to the minus 3 kilogram per meter. Okay, I'm calculating it because in part B, I want to calculate the power. Okay, so I will use the power is equal half mu times omega square times A square times V. And here V is the speed of the wave. It's not the volume. Okay, so you need to pay attention. So this is half mu, which is 6.32 e to the minus 3 multiplied by omega. Omega is 2 pi f, so it is 2 times pi times f, and I have f is 60. Okay, and this is a square times the amplitude square, and the amplitude is 0.005 square times the speed. Okay, times the speed. I need to calculate the speed. It's a square root of tension, which is given 7.5 divided by mu, which is 6.32 e to the minus. Now I just use the calculator because this is just a calculator thing. You will get the value using the calculator 0.39 watt. Okay. Now, if the power output stays constant, but the frequency is doubled, what is the new amplitude of the wave on the wire? Let me erase a little bit. So, P prime is equal to P, okay? And they say like this, the power output stays constant. It means P prime is equal to P, but the frequency is doubled. So P prime, which is half mu omega prime square times A prime square times V, this is equal to half mu omega square times A square times the speed. Okay, now a few things will disappear here because I have half here and half here. I have a mu here and a mu here. This is the same linear mass per unit length. And then I have V here and V here. All these will disappear. What am I left with is omega prime square times A prime square. And it's telling me that this is 2 times pi times f prime, all of it square, times A prime square is equal to omega square times A square. Okay, instead of omega, I will put 2 pi f. And now I will come here and I will put 2 times pi times f prime is 2f because they said it is doubled. Okay, so times a prime squared. This is equal to 2 times pi times f squared times a squared. Now, here I have 2 pi f. I will keep it inside, but I have a 2 here next to the f. I will get it outside. 2 squared will be 4. So 4 into 2 pi f squared times a prime squared is equal to 2 times pi times f squared times a squared. Now I can delete this 2 pi f squared by 2 pi f squared. So I will be left with 4 a prime squared is equal a squared, or a prime squared equal a squared over 4 implies a prime is equal to a over 4. So if I double the frequency, the amplitude will be halved. Okay, and with this I reach the end. Let me double check. I reach the end of today's lecture. Yes, I reach the end of today's lecture and the end of this chapter. So if you have any questions or concerns, just send me an email and I will get back to you in the live session or in next lectures. Bye-bye.